Hello everyone, welcome to our talk about the power of synergy in differential privacy, combining a small curator with local randomizers. This is joint work with Amos Beimel, Aleksandra Korolova, Kobbi Nissim, and Uri Shtemer, and myself, or Sheffet. This is work that the bulk of it was done when we were all at the Simons Institute, and I am proud to present this work at the very first ITC conference. Okay, this work is about differential privacy, a notion that I assume by now most of the viewers of this video are aware of. The important thing to note here is that this notion is information theoretic. It is a statistical property that an algorithm needs to satisfy regardless of computational assumptions. This is a notion that defines how to protect individual level data while conducting large-scale data analysis. Formally, we say that an algorithm is epsilon differentially private, and we quantify the privacy loss by this parameter epsilon if for any two neighboring datasets that differ just on the details of one certain person, the probability of any event occurring on the output of the algorithm is roughly the same between these neighboring datasets. It can change by at most this small multiplicative factor e to the epsilon. In this talk, we're going to focus about differentially private algorithms that also happen to be alpha-beta PAC learners. Namely, they are always epsilon differentially private, but assuming that the input also satisfies the following properties, such as each entry is sampled IID from a distribution, and each entry is actually composed from a vector of features x joined with a label. Then, with high probability, the algorithm returns an hypothesis that classifies each new, freshly sampled from the same distribution vector of features and gives it a label that, with only a small probability, alpha, errs and deviates from the true label. Now, in the field of designing differentially private PAC learners, we ask ourselves, what is the sample complexity for private learning? Namely, we have this parameter of loss epsilon, we have this parameter of utility alpha, how much error we are going to allow, and based on these parameters, we ask ourselves, how many points sampled IID from our distribution must we see? Notice that I've omitted beta because throughout this talk, we're going to assume that beta is a fixed small constant. Okay. Far too great of a literature on differential privacy, on differentially private learning to survey by now. But one particular result that I want to talk about talks about the problem of learning threshold functions. Namely, the input is a d-bit input. It represents a number between 0 and 2 to the d minus 1. And the labeling is given by some true parameter t such that all points below this t get the value 0, and all the points above this value t get the value 1. It is known by previous works, joint works, actually there's quite literature about this, but it is known that any PAC learner for this threshold function requires sample complexity that is at least proportional to d, log the size of the domain. Note, in our domain, or the number of possible functions is 2 to the d, our domain is of size 2 to the d, we require at least d samples. But this is done in the curator model. In the curator model, we are the trusted curator. We are the doctors. We represent the hospital. We have access to the true details of n individuals, and we analyze them, and we output something that preserves privacy. In contrast, and in order to avoid the creation of a single dataset that is exposed to hacks, there exists the local model. In the local model, each individual randomizes her own answers in a protocol in a way that the view of that individual does not on the responses of this one individual does not change drastically if she changes her details. It is a very strong property that I'm not going to word here formally, but basically it is a protocol, something that many in the cryptographic community are well acquainted with. This trust-free model prevents us from knowing or putting all eggs in a single basket, the one of the curator. It is a trust-free model. No one needs to trust anyone. I can just randomize my own answers and control my own replies to the protocol. And a canonical lower bound, again, a long series of work culminated in the work of Joseph et al., is that to estimate the average of n users up to alpha, namely each user is some number between 0 and 1, and we want to estimate the average up to some error alpha, this requires us to have at least 1 over epsilon squared alpha squared many examples. Another canonical result, again culminating in many works, but the very first one was the work of Kasiwanathan and al. About what can be learned privately, who showed that in the local model, in this model where there is a private protocol, everything we can learn is basically any function within the statistical query model, which it can be learned in the statistical query model. I am not going to go into the full details of what is a statistical query model, but another key result of it from Blum et al. Is that parity, the parity function the set of parity functions cannot be learned in this SQ model. And what are the parity functions? Well, these are all the hypotheses that take a d-bit random string and do dot product with another random string r. They are characterized by this random string r, and they do dot XOR or dot product modulo 2. And basically, we cannot learn the parity function. We cannot learn what is the function hr that gives the labels to the points in our data set, to the points of our users, sorry, if unless the number of users is exponentially large. Now, in this work, we leverage on a previous work of Avanet et al., who proposed combining these two models, namely taking a protocol for n+1 users. N of them are standard local model users, whereas 1 is essentially a small curator. It is a curator that knows the details of m additional individuals. And now, once we have given this power, additional power, to one of the people participating in the local model protocol, we ask ourselves, what can be learned in this model? Now, we're going to make two key assumptions about this model that we're studying in this work. One is that the curator is small. It's not small in the sense of being a small person. It is small in the sense that knowing very few individuals in comparison to the rest of the people participating in the protocol. Namely, if the curator knows m people, then m is much smaller than n. Another assumption that we're going to make in this work is that all individuals, all m plus n individuals, are drawn from the very same distribution. Namely, those who go to our hospital and those who participate in the trust-free model computation are all taken from the same distribution. And that is what we study in this work. We study the hybrid model. We ask ourselves, what can be learned in the hybrid model, which is essentially new? It cannot be learned in the local model. And of course, we want to quantify under what regime of parameters do we need. Namely, again, it's the same question we always ask ourselves in the design of differentially private algorithms or protocols. We have the parameter epsilon of the desired privacy loss. We have the parameter alpha of the desired accuracy loss, and we ask ourselves how many individuals, n and n, do we need in order to solve the problem and basically do better than a naive, quote-unquote, local model protocol. Again, this is a quantitative question. That is why we ask ourselves, what is the regime of parameters? Now, despite the fact that I've drawn here epsilon and alpha, actually, the parameters that we're going to look at are going to be quite different. The size of the domain, how many points are needed, but also in regards to how many iterations and levels of computations. Namely, can we ask the curator and the local model questions in parallel? Do we need one of them to take the first step and only then ask the other party question? And so on and so forth. Okay, so far I have given you the background on differential privacy and asked the meta question of this work: what is the cost of learning in the hybrid model? From here on, I'm going to give the very first example, select then estimate. And then I'm going to move to a negative result because cryptographers like negative thinking. And then I'm going to give or talk a little bit about the positive results we give for a variety of functions, more contrived or less contrived, depending on how you choose to look at it. Lastly, I'm going to present some directions for future work. Okay, so let's see the very first example in which we do better than a naive protocol. We call this alpha select and alpha prime estimate. We have n plus m individuals. Each of them have d binary features. And our goal is to find a feature with fairly large mean compared to the largest one, and then estimate the mean up to a tighter accuracy. Namely, we are given two parameters, alpha prime and alpha. Alpha prime is the smaller one. We find a dominating feature. In comparison to the highest mean, it is not that far off. It is only alpha far off from the highest mean. Given that we have chosen feature I, we wish to estimate its mean up to alpha prime accuracy. I should say that this work is actually motivated by a very popular task in genomic studies of finding the most predominant feature. Okay, so there is a naive hybrid model protocol for this. The curator is in charge of finding this feature, and this also only requires roughly log d features. Oh, sorry, log d samples. Whereas in the naive model, it would have required us d log d samples. This is a bound given by Ullman in his work. However, it is only a lower bound that holds for non-interactive protocols. We prove this bound, we improve on this bound for any kind of protocol and give roughly a bound of, which is polynomial in d to the cube, 1 over 3. D to the third. Okay, so the curator is in charge of finding the feature. Then, once this feature is published, the local users are the one that are in charge of producing the mean estimation up to up to alpha prime accuracy, and this requires, as we've discussed before, 1 over alpha prime squared epsilon squared. And comparing to the naive local model baseline, we infer that we do better with fewer individuals when alpha prime is within a certain regime, when the ratio between alpha prime and alpha ranges from 1 over square root of d to 1 over log d. Okay, so let's talk about a negative result now. Suppose we have m plus n individuals and each one of them is a number, its details is a number between 0 and 1, and we want to estimate the mean of these m plus n individuals, m plus n values, up to an error of alpha. There is one lower bound that we've already There is one lower bound that we've already discussed in the local model. There's another one for the Curator model. And basically, we show in our work that we cannot improve on these lower bounds. Namely, there does not exist an MN hybrid model protocol for learning or estimating the average of n plus n users up to an error alpha unless m or n meets those lower bounds. Namely, we cannot do better unless we do it purely in the Curator model or purely in the local model. Just to give intuition about this result is basically we already know that to estimate this number in the local model requires roughly an error of 1 over square root of n. And since m is much smaller than n, then these individuals that were sampled in the Curator, into the Curator's dataset, they have standard deviation also of about 1 over square root of n. That is why we cannot overcome the obstacle of 1 over square root of n. That is why we cannot improve on this lower bound. Again, it's not the formal proof. This is just an intuition. Okay. I am now switching to this strain of positive results regarding functions that basically these are functions that we have designed, as opposed to thus far where we talked about estimating the mean and it was a canonical task. These are more tasks that we came up with. The first one is a concatenation of parity and threshold. Namely, each data point is composed of two separate vector features, x and y. X has C bits and y has B bits. And two separate labels, L1 and L2, where L1 corresponds to a parity and L2 corresponds to a threshold. And as ever, our goal is to learn this pairwise classifier. Let's think of it as giving a label which is between 1 and 4, of one of 4 possible labels. And our theorem is such that when b, the length of the y's, is roughly squared in the length of the x's, m is so and so and b is so and so, then in the MN hybrid model, we can learn this function. Basically, the Curator learns the parity, the local model users learn the threshold. However, we show that no Curator model algorithm or local model protocol can learn this pairwise classifiers, this concatenation of two classifiers, because they simply do not have enough points for their domain size. Had there been such a protocol, we could reduce it to learning just the parity in the local model or the threshold in the Curator model with less than its desired sample complexity. Okay, this is an easy result. Let's talk about our second example in which we XOR a parity and a threshold. Again, each feature, each example is composed of these two feature vectors, a C-bit long x and a B-bit long y. Again, we have a parity with some unknown r and a threshold for some unknown threshold t. But the actual label given here is the XOR of this parity and threshold. What we show is that, again, in a certain regime of parameters, and from now on we're going to fix epsilon and alpha as small constants. In this regime, there exists an MN hybrid model protocol that learns that XORed classifier, and it is doing that without any interaction. We'll talk in a minute about how to do that. But we cannot learn it either in the Curator model or in the local model. Again, we could very easily reduce it to a problem where we only learn threshold in the Curator model or parity in the local model. Now, this algorithm is fairly interesting. How does it work? It works in the following way. Again, the key point is this algorithm is not iterative. We don't ask the local model users first something and then the Curator model something. No, both of them learn in parallel. What do they learn? Well, the local model users actually learn the CDF of Y, or basically they learn this what we call alpha threshold. They learn where do the threshold T1, T2, T3, T1 over alpha lie, such that in each bucket between two consecutive thresholds, there exists alpha probability mass of the distribution over the Y's. They learn these, they send this to the referee. The curator, well, it learns only the parity function, but she doesn't learn a single parity function. She learns 1 over alpha parity function. She produces these different H1, H2, H3 up to H1 over alpha. Each one of them is a different parity. And where does she learn it? She learns it over her own buckets. She has access to the details of individuals, so she first sorts them according to the Y values, partition them into buckets. In each bucket has alpha fraction of its own, of her own M individuals. And from that bucket, it learns the parity corresponding solely to the examples that fall into this bucket. Now that we have both of these thresholds and this hypothesis, the key point here is that the threshold for L2, the threshold function, falls exactly in one of these buckets. So for any other bucket except that one, that parity is a good classifier because that bit of being greater or smaller than the threshold is fixed. So it's basically like learning parity. So that is the function we release to the world. The hypothesis over H that takes both over this feature vector of both X and Y. What do we release? We look what bucket, in what fraction of the threshold does the Y lie. If it falls into bucket I, then we take hypothesis I and we release it over this X. That is our learner. It is an improper learner. It's an interesting question whether there exists a proper learner from this domain that does so without any interaction. The third and fourth positive results are far more advanced, and I'm only going to describe the problem setting. The third result is about a function called 1 out of 2 to the d parities. Okay, in advance, we fix these different C-bit strings. The first, the second, up to 2 to the d such different strings. Each one of them gives a different hypothesis for a parity. Then we pick some secret S, which is of size d, it has d bits, and we do an m plus 1 secret share. More formally, it's m plus 1 out of m plus 1 secret sharing. And we divide this as S1 up to Sn plus 1. This is what we do in advance. Now let me describe the distribution from which the samples are taken. And it is a half-half distribution. With probability half, we release a string which is a uniformly at random chosen X of length C with only C bits, and all of its 2 to the d different parities with the first random string, with the second random string, with the third, and so on and so forth until the very last one. That is one kind of examples we release. The other kind, with probability half, we release an example where we sample a share uniformly at random out of the m plus 1 possible shares, and then we release the number of the share as well of its secret. Okay, so what do we argue about this problem? In this problem, our goal is to find the RS secret. Out of all 2 to the d parities, we're interested in learning one. The one which is indexed by S. We wish to do it from m plus n individuals sampled from P. And what we show is that in a certain regime of parameters, this can be done, okay, provided we are doing a protocol where the local agents are the one that move first. And how does this protocol work? Where it's very simple. There are only n+1 secrets, and there are many local model users. So they do what is known as heavy eaters, basically do a histogram and return the values that appear most commonly. There will be, with really high probability, these n+1 values that appear most commonly, and those are the ones that they release to the world. Now that the local models have learned all n+1 shares, we XOR them together, we find S, and now the local and the curator has enough points in her dataset to learn the parity indexed by this secret S. So the protocol, once we know the local models move first and learn the secret, is very straightforward. However, we show that if it's the other way around, namely if the curator is the one that moved first, then the sample complexity is exponential in D, and basically, because D is log C, is a really high polynomial in C, far higher than the one we have here, which is roughly C squared. And moreover, we cannot learn this purely in the local model or the curator model. In the local model, if we have exponentially many users, in the curator model at all, because the curator has access to m individuals and we have n+1 secret shares. The reduction to show the other 2 points is very complicated and long and really hard to find a one sentence long way to describe it. So I can only refer you to the paper. Lastly, we are going to talk about sort of the symmetric analog of the previous problem. We call it Parity-Chooses-Secret. In advance, we fix this C-bit string R. This is our parity. And then we have 2 to the C different secrets. And each one of them further we're doing a secret n+1 secret share of the secret. The distribution is such that we sample a uniformly at random chosen X, and then we sample a secret, uniformly at random secret share. What we do is we release X and its XOR with the true parity R, and the TIFF share of each of the 2 to the C secrets. Our goal, of course, is to find the rth secret. Now, again, we show that under a certain regime of parameters, in the hybrid model, there exists a protocol to learn or to find the rth secret, where the curator is the one that moves first. The curator just learns the parity R, releases that to the local model users. They do the heavy eater for the rth. Among all 2 to the C features, they focus only on the rth secret and learn those n+1 shares, do the XORs, and recover S. But we also show there is no protocol where the local agents are the one that move first. And if we do it just in the local model, we have to do it with n, which is exponential in C, rather polynomial in C. Okay, so to conclude this work, we think that this is an interesting, exciting new direction for research. It joins a variety of other works that append the local model with a different construction. Most commonly, the shuffling model adds a random shuffler of the n individuals. We are wondering if there's a unifying framework, namely if we can give some high-level characterization of tasks where the number of local model users decreases significantly from n to n prime, where we add to them this m size curator. And two concrete issues that we don't deal with is that first, all of our results talk about epsilon differential privacy versus the approximate epsilon delta differential privacy. So extending that from epsilon to epsilon delta is non-trivial at all, because very weak lower bounds are known about epsilon delta differentially private learners. The second question is also intriguing. What about selection bias? What about the fact that these are not hospital patients? Some of them go to my hospital, some of them are there in the population. How about a selection bias? People opt in to join to the curator because these are the people that trust the curator, and so by creating some selection, this is not the same distribution. There are two different distributions: those who opt into the data set of the curator, those who remain local model users. Can we do transfer learning? Can we design hybrid model transfer learning protocols? With this, I will conclude. I'm far away over my time. Thank you very much, and that is it.